Problems with gravitational fields. Question 1. Find the force of gravitational attraction between a 60 kilogram mass and a 70 kilogram mass separated by 2 meters. Right, to do this we use the standard formula Fg equals G, big G, times the big M times small m, all divided by r squared. And that's the one there. And if you punch in the numbers correctly in your calculator, you should get 7.0 times 10 to the negative 8 newtons as your answer. If not, then you need to practice using your calculator because it is really that simple. Question 2. At what speed must the satellite be travelling so that it can remain in a circular orbit at 1,600 kilometres above the surface of the Earth? Now we're given the mass of the Earth, that's ME, at 5.98 times 10 to the 24 kilograms, and the radius of the Earth at 6.40 times 10, that should be to the power of 6 meters. Now to do this, you need to start by equating centripetal force Fc and the gravitational force Fg. And so if you do that, you have mv squared over r for your centripetal force equal to the big G, big M, small m over r squared for the gravitational force. Of course, the m's, the small m's that is, cancel out, and pretty soon you can derive the equation after a bit of rearrangement. V equals the square root of big G, big M over r. Now, if you're careful with your calculator, once again, you punch in big G as 6.67 by 10 to the power of negative 11 into this equation. The mass of the Earth and the radius of the Earth, you should get as your answer 7.060 meters per second. That's the 3 significant figures. Notice all the figures given to 3 significant figures. We assume that one is 2. Okay, question 3. A communication satellite is to be placed in a circular geostationary orbit. Find its speed and height above the Earth's surface. The mass of the Earth is given, and so is the radius, as it was before. Now, to do this, the first thing to realize is the period of that satellite in that geostationary orbit must be 86,400 seconds, because that's 1 day. It takes 1 day to go around. That way it will stay exactly above the same point on the Earth's surface all the time. Now to do this we need to approach it in a certain way. To find the height or the radius of orbit, first of all, we can use this period 86,400 seconds and the fact that to go in a circle of radius r, the speed of the object must equal distance over time, and for a circle, of course, the distance is the circumference, 2 pi r, and in this case the time is 1 period. And of course we also have another expression for speed for a satellite in orbit, and we can equate the 2 expressions. The other one is the gm over r all square rooted equation. And so now we can just look at rearranging and solving for r, making r the subject of this expression here. Now if you have rearranged that successfully, you should end up with an expression involving r cubed, something like this. R cubed in your expression should equal G, big M, big T divided by 4 pi squared. So that's quite an expression. To find r, we need to take the cube root of the left side. So we can do that as follows. And with an eraser I can just rub off that cubed. There we go. So that's our final expression for R. Next you have to plug in the numbers very carefully. For big G, big M, 86,400. Oops, I think I missed a square somewhere. There we go, must be squared. And of course 4 pi squared. So once you calculate that, you should get as your answer for the orbital distance from the center of the Earth 4.225 times 10 to the 7 meters. Now that is not the height above the Earth's surface, that is just the orbital radius. So to get the height above the Earth's surface, h, we need to have that number and subtract the Earth's radius, 6.4 million meters, and you should then get the final answer of 3.59 times 10 to the 7 meters above the Earth's surface. Okay, so it's a 9. Next we'll find the speed of that satellite in that orbit, but of course to do that we're going to use this orbital distance in our calculation. So that's on the next slide. And we revert to this expression, big G, big M over R, all square rooted. Plugging the numbers in carefully, 6.67 times 10 to the negative 11. For big G, 5.98 times 10 to the power of 24 for the mass of the Earth. And the orbital radius we just found, 4.225 times 10 to the power of 7. Taking the square root of that expression, you should find you get 3,100 meters per second. The two significant figures. Question 4. This is from November 2008, paper 4. A small object of mass, small m, rests on the equator of a planet. The surface of the planet exerts a normal reaction force on the mass. A. State formulae in terms of big M, small m, big R, and now that should be omega. 4. Part 1, the gravitational force between the planet and the object. Now, of course, that's straightforward, it's just Fg as you know it. Oh, except they want us to use a big R here. Squared. Easy. So 4 continued, the part 2, with those same symbols, they want you to write the expression for the centripetal force required for circular motion of the small mass. Now, hopefully you can recall from the first topic a bit of some of the equations for circular motion, in which case you may already know that it's just mr omega squared. If you have forgotten that stuff, you need to remember what's useful. I think V over R is omega, and since Fc is mv squared over R, we can write Fc as mr omega squared. That's the force in this case. And lastly, for part 3, they want us to write an expression for the normal reaction exerted by the planet on the mass, and that would be equal to the gravitational force subtracting away the centripetal force, since that centripetal force would be used purely to keep the object moving with the planet in a circle at the orbital speed of the planet itself. So we'd actually write this in terms of those symbols, Gm, that's big M, small m, over big R squared, minus mr omega squared. Whoops, I just noticed I made a boo-boo there. That should be a big R.